Hello, it's Mr. Causality here, and today we have a very special PowerPoint lesson that we're going to be going through. So you can just follow with the PowerPoint if you like, or you can follow along with this video, which is me narrating the PowerPoint. As we go, you're going to fill in your lesson as normal, but you'll notice that anything I want you to fill in on your page is written in red in the PowerPoint presentation. So hopefully that makes sense. Today we're going to continue learning statistics, but now we're going to change. The first half of this chapter was about univariate analysis, which is when you have one piece of data. For example, how tall a student is. Now we're going to be looking at bivariate analysis, which is when you compare two statistics. So for example, when you compare how tall a student is compared to how much broccoli they eat every day. So we'll start off. This is a nice little intro. I get a lot of flack though every year about this diagram. This is you can see there are two variables here. The first is the difficulty to eat the food or the fruit, and then the second is the tastiness. So you can see you have some fruits that the person who made this believes, like peaches, which are very tasty, very easy to eat, compared to grapes, which are very tasty, but because they have seeds are slightly more difficult. Compared to watermelons, which, again, the person who made this diagram, they think that watermelons are only medium tastiness and actually sort of difficult to eat. And then grapefruits, difficult to eat and not very tasty. Again, that's someone's opinion. But you can see how we can measure every fruit with these two qualities, these two pieces of data, and you can compare them on a graph. That's the theme of the next 3 lessons in this chapter. So there we are. The first branch of statistics was univariate data. That's when we look at one piece of data. This chapter, bivariate data, which contains pairs of data. You can see this should be in red. This is in red, so it should be written on your page. So there's my classic example: height of each student and the amount of vegetables they eat every day. Does vegetables make students taller? Well, we have to look at the data and see if there's any truth to that. So that's what we're looking at now. We're interested in this question: how are the two pieces of data related? How does vegetables affect height? Another way we call this relation is correlation. So when you hear that two pieces of data are correlated, we're talking about how they're related. How does one impact the other? Let's continue. So here we go. Oh, I use this. I guess this is why I like this example so much. I use it every year. What is the relationship between the amount of vegetables eaten every day and height? So what I did is I sampled 1,000 students. I collected all this data. So each student, I got 2 pieces of information from: the grams of the mass of veggies that they eat every day, and their height. So there's all my data. I have 1,000 data points. It's a lot of data. So now what I want to do is I want to graph all this information on a scatter plot. Now you need to basically choose for each of these 2 variables. One is going to be your x, one is going to be your y. Your x, as you've seen in science and other courses, is your independent variable. It's traditionally the thing that you can control. And then the dependent is your output, or your y variable. So I'll put veggies on the x and I'll put height on the y. And then we might get different, the graph might resemble any one of these, right? Depending on the relationship. So it could be this, it could be that, whatever. But what I want you to be able to do is discuss the relationship when we see it. So if you have something like this where basically, remember I said x was vegetables. So as you eat more vegetables, the height gets higher, right? This kind of positive relationship. So one thing goes up, the other goes up. When all the dots are going in and they make a positive slope, we say it's a positive relationship. Now, because the dots are so close together, that shows me it's a very strong relationship. So we call this strong positive. Now there's an R value. We're going to learn the value. We're going to learn the R value in a few lessons. I just included it here for your information, but this is not something that we're going to need to know yet. Now over here, I see there's a positive relationship. As one goes up, the other goes up, but it's not as strong. It's more spread out. So the results are not as definitive. Student eats vegetables. This student, ate some vegetables, and they're pretty short. And then the student up here ate the same amount of vegetables. They're pretty tall. There's quite a range, so it's not as strong a relationship. We say it's a moderate positive. And then you have something like this where it's almost meaningless. Like the dots are almost everywhere. There's a slight positive, positive correlation, but for the most part, they're spread out. Similarly, you could have a negative relationship. This means that as one thing goes up, so as the number of vegetables I eat goes up, the height of the student goes down. So actually, vegetables are causing students to be shorter. This would be very strong negative, moderate negative, and again here, it's sort of negative, but so weak it barely looks like anything. I imagine for our case, vegetables and height, probably these two things are unrelated, right? Like it's unlikely that eating more vegetables causes you to be taller. Now, I don't know that much about biology. You can prove me wrong. You could do a study on it, but my guess would be that it's a pretty weak relationship. In this course, we're going to study these relationships, these correlations. We're actually going to study linear correlations, which is when the data correlation resembles some sort of line, so linear correlation. But just so you know, there are other sorts of correlations. You could have data that when you graph it, looks like a parabola, a parabolic relation. You could have a situation where you graph a bunch of points and it has some sort of log function that can fit to it. Those exist. Your calculator and Microsoft Excel can analyze things like that, but linear is what is in this course. I just want to show you a TED Talk I show every year. This is one of the original TED Talks that I saw when TED Talks first started when I was in university. But it's good because it shows the idea of taking two variables and analyzing the correlation and seeing what you can learn from that correlation. So this is Dr. Hans Rosling from Sweden and his study of UN statistical data.
About 10 years ago, I took on the task to teach global development to Swedish undergraduate students. That was after having spent about 20 years together with African institutions studying hunger in Africa. So I was sort of expected to know a little about the world. And I started in our medical university, Karolinska Institute, an undergraduate course called Global Health. But when you get that opportunity, you get a little nervous. I thought these students coming to us actually have the highest grade you can get in Swedish college system. So I thought maybe they know everything I'm going to teach them about. So I did a pre-test when they came. And one of the questions from which I learned a lot was this one. Which country has the highest child mortality of these 5 pairs? And I put them together so that in each pair of country, one has twice the child mortality of the other.
Okay, I'm just going to pause. So he is at, because he doesn't pause in the video, which country has the highest child mortality? Let's see how you fare with this little quiz he had. So of these pairs, can you circle the one that has the highest child mortality? Sri Lanka versus Turkey, Poland or South Korea, Malaysia or Russia, Pakistan or Vietnam, Thailand or South Africa. So think about those for a second. Think about what your answers would be. And now let's see what he says.
And I put them together so that in each pair of country, one has twice the child mortality of the other. And this means that it's much bigger the difference than the uncertainty of the data. I won't put you at a test here, but it's Turkey, which is highest there, Poland, Russia, Pakistan, and South Africa. And these were the results of the Swedish students. I did it, so I got a confidence interval, which was pretty narrow, and I got happy, of course. I had 1.8 right answer out of 5 possible. That means that there was a place for a professor of international health and for my course. But one late night, when I was compiling the report, I really realized my discovery. I have shown that Swedish top students know statistically significantly less about the world than the chimpanzees.
Students, this is their mean. They got 1.8 right, so less than 2 right on average, right? That's the mean. Now, the confidence interval, think of that a little bit like you'd think of the spread or the standard deviation. So that's how confident we can be with the number 1.8. So it might be plus or minus. So it could be 2.2 to 1.4, right? It's plus or minus 0.4. So that's kind of the idea of the confidence interval. But essentially the mean was 2. Now, chimpanzees, this is a classic idea in math about if you wanted to choose something at random, you would put the 2 options or up on the wall, and you would give the give like a monkey or chimpanzee some darts and get the chimpanzees to throw the darts at the thing on the wall, and whichever one the dart hit would be the one that they chose. And if you had that situation, it would be the chimpanzee would be correct 50% of the time because they're choosing at random. So if you have these 5 questions, chimpanzees choosing at random, the chimpanzee is going to be right, or 2.5 out of 5 times, right? 50% of the time, which is better than the students. So his point is that you're better off guessing randomly than trying to answer thoughtfully, because random is better. The score is better.
I have shown that Swedish top students know statistically significantly less about the world than the chimpanzees. Because the chimpanzee would score half right. If I gave them 2 bananas with Sri Lanka and Turkey, they would be right half of the cases. But the students are not there. The problem for me was not ignorance, it was preconceived ideas. I did also an unethical study of the professors of the Karolinska Institute that hands out the Nobel Prize in medicine, and they are on par with the chimpanzee there. So this is where I realized that there was really a need to communicate, because the data of what's happening in the world and the child health of every country is very well aware. So we did this software which displays it like this. Every bubble here is a country. This country over here is China. This is India. The size of the bubble is the population. And on this axis here, I put fertility rate. Because my students, what they said when they looked upon the world, and I asked them, what do you really think about the world? Well, I first discovered that the textbook was Tintin mainly. And they said the world is still we and them. And we is Western world, and them is third world. And what do you mean with Western world? I said, well, that's long life in small family. And third world is short life in large family. So this is what I could display here. I put fertility rate here, number of children per woman, 1, 2, 3, 4, up to about 8 children per woman. We have very good data since 1962, 1960 about, on the size of families in all countries. The error margin is narrow. Here I put life expectancy at birth, from 30 years in some countries up to about 70 years. And 1962, there was really a group of countries here that was industrialized countries, and they had small families and long lives. And these were the developing countries. They had large families and they had relatively short lives. Now, what has happened since 1962? We want to see the change. Are the students right? It's still 2 types of countries? Or have these developing countries got smaller families and they live here? Or have they got longer lives and live up there? Let's see. We start the world. And this is all UN statistic that has been available. Here we go. Can you see there? It's China. They're moving against better health. They're improving there. All the green Latin American countries, they are moving towards smaller families. The yellow ones here are the Arabic countries, and they get larger families, but longer lives, but not larger families. The Africans are the green down here. They still remain here. This is India. Indonesia is moving on pretty fast. And in the 80s here, you have Bangladesh still among the African countries there. But now Bangladesh, it's a miracle that happens in the 80s. The imams start to promote family planning, and they move up into that corner. And in 90s, we have the terrible HIV epidemic that that takes down the life expectancy of the African countries, and all the rest of the world moves up into the corner where we have long lives and small family, and we have a completely new world. Let me make a comparison directly between United States of America and Vietnam. 1964. America had small families and long life. Vietnam had large families and short lives. And this is what happens. The data during the war indicate that even with all the death, there was an improvement of life expectancy. By the end of the year, the family planning started in Vietnam, and they went for smaller families. And the United States up there is getting for longer life, keeping family size. And in the 80s now, they give up communist planning and they go for market economy, and it moves faster even than social life. And today we have in Vietnam the same life expectancy and the same family size here in Vietnam 2003 as in United States 1974 by the end of the war. I think we all, if we don't look in the data, we underestimate the tremendous change in Asia, which was in social change before we saw the economical change. So let's move over.
Okay, thank you, Dr. Hans. That's a great, I really like how he does a play-by-play as you do. Oh. I really like how he does the play-by-play, and he's a real character, and he's gone on to do a lot of more modern TED Talks since then, and he likes to really show you how data, comparing two variables, you can really analyze trends. Notice that on the X and Y axis, there is no time, right? Each year is a point with two statistics, and then he graphs, and for each country, and then he graphs them all, and you see the process over time. But this is really literally two variables. What did he do? You know, this one here, we can see child mortality versus fertility. So this is, I bring this up too because you guys are going to be doing an IA or a exploration paper for math, and a lot of you will do some sort of study using statistics. And this is a great website, his website, Gapminder, or the UN website. You can get some data and you can do an analysis like he just did. So it's a good thing for us to see and discuss. So your homework for today is pretty straightforward. It's page 337, number 1 to 3. You're just going to be using some of the terminology that we explained earlier in the lesson. So it's pretty quick. But I did want to continue in this lesson. This is a bit of a TOK, but it's a really important one. So I'll never take it out of the course, even if we are strapped for time because of coronavirus. But this is the idea of correlation and causality. So you can just watch. There's not much to write down, but you can just kind of look at the point that we're trying to make here. First of all, the idea that statistics can be used to deceive people is something that we should be aware of. And, you know, this is not new. So, for example, these are from Fox News, which I don't know if you want to call it a news source, but this is a real image that people would see on TV. So this was when President Obama was, I guess, sometime during his tenure. And Fox News says, wow, look at the employment rate under President Obama. And so you can see it over the months of 2011. And what you might think, like looking at it, is like, oh wow, look at the big dip that happened here. What happened? What did President Obama do? Or you might see the 8.5 average and say, oh wow, President Obama's unemployment rate is so high compared to the average, 8.5. That's how statistics can be used to deceive. Because really, look at this this unemployment rate, 9, 8.9, 8.8, 9.2. It's essentially 9 the entire time. Like graphing this is sort of unnecessarily making some peaks and valleys that aren't really peaks and values at all. Also consider that if the average is 8.5, well, the fact that the unemployment was at 9 or 9.2 is, again, not very far a difference. This graph makes it look like, wow, look how high, or sorry, this graph makes the viewer think that, oh, under President Obama, the unemployment's been so high, when really, because of the scale of the y-axis, we're being tricked a little bit. Another one here, again, there was a lot during the Obama era. So this is the Bush tax cut. So this is tax cuts that President Bush made. And we're saying when they expire, so now the taxes are at 35%. When they expire, your taxes are going to go way up. Oh no, that's so terrible. But then again, when you look, 35% to 39.6. This makes it look like they're going from 5% to 90%. But again, the scale of this graph is designed to trick the viewer. Right? It's designed to deceive. Note that there's no lie in either of these charts. The presentation, though, is meant to deceive the viewer. This is one other one I like to show. You hear, oh, Sensodyne. 9 out of 10 dentists recommend Sensodyne. I've heard that the way that they come with the statistic is they give a bunch of dentists a survey of all the possible toothpaste out there, and they say, check off the ones you recommend. So the dentists check off like a dozen toothpastes, and then the Sensodyne looks at the data and says, oh, well, 90% recommended ours, which is true, but 90% probably recommended all the other ones too. So it's kind of a little bit deceptive. So this is how statistics can be used to deceive people. But there's an even more sinister way that we can mislead people with statistics, and that especially comes up with bivariate statistics. I'll use this example, and this is a very classic example, a very classic chart. It's a little bit of a backwards chart, so it's hard to it's a little bit weird to look at because the x-axis is actually decreasing. So forgive me for the weird chart, but this is a classic idea, which is if you look at this graph, you see that x is the number of pirates. So we see the number of pirates is going down. And what happens? This is the y variable. So as the number of pirates is going down, the global temperature is going up. Global warming. So when you look at this graph, you're led to believe, hey, we've got it. I know what's causing global warming. There's not enough pirates. As we've lost pirates in the world, the global average temperature has gone up. So we just need more pirates and the temperature will come back down. This is the major idea of this TOK talk. This idea that just because two things are correlated doesn't mean that one causes the other. So just because I can look at the way that the line has a positive correlation, that doesn't mean that there's causation. Here are some more, and again, this is real. So this one's actually from CNN or something like that. No, maybe it's not. I forget. No, it's just someone made this. This is the fresh lemons imported to the USA from Mexico. So as the US imports more lemons, what happens to the fatality rate or the number of deaths on the US highways? Well, as the number of lemons increases, the number of deaths goes down. Again, I'm pretty sure that lemon imports is not causing highway fatalities, but the graph leads you to believe otherwise. This is a little more fun. The chocolate consumption per year, per person, and the number of Nobel laureates per person. The Nobel laureate is someone who wins a Nobel Prize. So you have a country like Switzerland, they eat a lot of chocolate, and they win a lot of Nobel Prizes. You have a country like Finland, they eat some chocolate, but they don't get very many Nobel Prizes. And you kind of see this relation, right? As you eat more chocolate, you get more Nobel Prizes. If China wants more Nobel Prizes, they just need to eat more chocolate. So those are kind of fun, but now these are actual real-life charts. So this is from the Globe and Mail, a reliable Canadian newspaper. This is the obesity rate, and this is the amount of the number of kilometers driven. So you see, as the obesity rate increases, we see that people are driving more. So we might be led to believe, oh, obesity is happening because people are driving so much, which is possible. It's possible those two things are true, but it's not definite. We can't just assume that one causes the other just because we see it in the graph. Sure, it's possible that people are more obese because they drive more. It's also possible that people are driving more because it's colder, or because their work is further away, or because gas is cheap, right? There are many different reasons why people could be driving more and why people could be, the obesity rate could be changing. So this is just a correlation. It's a nice correlation, but it doesn't mean that it's a causation, that one is causing the other. And this is where this is why I keep this lesson in, because you can suddenly get some very sinister applications of correlation versus causality. There's a segment of the population that believes that autism is caused by vaccination, and they're gathering data, and they can take data and plot it in a way that makes it look like there's some sort of relationship. So this is from some scary anti-vaxxer website. Numbers don't lie. The vaccines don't prevent illness; they create it. So I guess as the this is the number of studies, and this is the prevalence of autism or something like that. But just my point is that sure, statistics can be put together, and it can kind of trick us, but then it can trick us into something that actually hurts society. And we all kind of live in this age of what is truth and all this kind of fake news. In math, we've been teaching about it, in statistics for a long time, but now in the past 10 years, the idea of fake news is something that you guys have grown up with. You know it's out there, and you know that to just look at a chart and to say take it as truth is not something you should be doing. You should always be asking why, looking at studies, making sure your sources are reliable, right? I don't know if Autism Speaks is necessarily a reliable website. I should be going to a reliable news website if I want to really, or journal articles by doctors and researchers if I really want to investigate things. So, and here's just some information. I think it's on your page. So, for example, let's say you have ice cream consumption and drowning deaths. So this graph makes me believe that as you have more ice cream, more people drown. And again, it's not a lie. Like, this is not fake. This is not, someone didn't make up the numbers. These are all real numbers. But the problem is that the correlation is not the causation. So yes, probably people are eating more ice cream and there's more drownings because both those things happen in the summer. So some other variable is causing the ice cream consumption, the hot weather, and it's causing the drowning, well, hot weather and more swimming. So these two things are correlated, but they're both caused by something else. A confounding variable. This is the thing. So you might be asking, how can I know if something causes something else? Well, not in math class, you can't. And you can't certainly not know, you can certainly not know it from a graph. In math class, we can just look at a graph and say there's a correlation, but we can't explain the correlation. We have to explain what causes what. We actually would need a controlled experiment. There's another subject you study that helps you do this. It's called science. As you learned in science, science is not just biology, physics, chemistry. Biology is the idea that you can ask a question, design an experiment, test your hypotheses, and then make conclusions. That's what science is. So you take some variable you want to study, and then you change that. Well, let me give you an example. So yeah, you would want to run an experiment where you take a variable you want to study, change the values for that variable only, and then see what your outcome is. So for example, I want to know what liquid helps my plant grow. So the thing I'm going to change is the type of liquid. So I have to have 3 plants or many plants with everything the same. So the same amount of light, the same soil, the same height, the same growing conditions. The only thing I'm going to change is this one variable, which is the liquid. So then every day, at 8 o'clock, I'm going to feed every plant the same amount of liquid, but different. So a Coke, a juice, a water. The next week, I'm going to do the same. And we're going to see after 2 weeks, how does the height of the plant change, or how does the health of the plant change? That's how you can determine if one thing causes another. It's a controlled experiment where you only change one variable at a time. Now, it's easy for science, for biology, for certain subjects. It can be really tough in other situations. For example, economics or health. One example I bring up is because we have a young child, and we don't want our child to be allergic to peanuts. So there's a lot of, for a long time, the thing that doctors told you was don't feed peanuts to your child when they're really young, because they could have an allergy. But then actually researchers looked, and there was one country in the world where students weren't, or where children weren't getting peanut allergies, and it was Israel. And the question was, well, why aren't the children in Israel getting peanut allergies? And when they looked into it, they found that there's some, it's called a bamba. It's some sort of snack. It's like a bubble snack or puffy snack that has peanut butter in it, and that was being fed to kids at a young age just because it was a snack that was around the house. And as it turned out, because the children were eating this at a young age, they weren't developing the allergy. So because of that study, because we had one country where people were being fed peanuts at a really young age, and then all these other countries where they weren't being fed peanuts at a young age, we were able to kind of have a controlled experiment and see that, oh, the children who were being fed peanuts at a young age actually were healthier and didn't have the allergies. So nowadays, doctors say feed peanuts to your children really early. And fortunately, we feed peanut butter all the time to our little guy, and he's still not allergic, which is good. So it is difficult in some situations to do controlled experiments, and you see some really clever applications to try to figure things out. So here are some just food for thought. Are they causal or not causal? Does one cause the other? So bullying harms mental health. So sure, I could graph the amount of bullying and mental health, and they'd probably be correlated. But does bullying harm mental health? Yeah, probably. Like if you did an experiment, I would say bullying does cause mental health. Stress of watching major sporting events can be hazardous to the heart. So does one cause the other? Does sporting events cause heart problems? Yeah, maybe, but maybe other things cause heart problems more. Like I bet more heart attacks might have more to do with what you eat than whether you're watching major sporting events. Temperature and number of ice cream vendors out for the day. So as temperatures go up, sure, more ice cream vendors are out. Do you think that's caused, that those are one's causing the other? Most likely, but maybe, the price of ice cream has come down, so there's more ice cream vendors out. Maybe the gasoline prices have gone up, so there could be other variables. You'd have to run an experiment. TV raises blood pressure in obese adults. Maybe there's a correlation, but again, is TV raising the blood pressure? Probably not. It's probably something else that has to do with exercise and what you're eating. Deep voice men have more children. Ooh, wow, awkward. So is there a correlation? Maybe, but I don't think it just happens that deep voice men are having more children. It might have more to do with something else. It might have to do with, this might be a perception sort of thing. Watching too much violence on TV leads to people being violent in real life. This is a classic one. I remember when I was in high school, there was a big shooting at one of the first school shootings that people heard about at Columbine High School in the U.S. And this was the thing. It was like, oh, well, because of all these violent movies, that's why this happened. And this was a real thing. And it kind of makes you wonder, well, is it true? Like, I mean, I play video games sometimes. I'm not a violent person. So, I definitely think that this might be correlated, but I don't think that's necessarily the reason why people are violent. But I could be wrong. Surgeons with video game skills perform better in simulated surgery. Yes, again, so this could be related. But is one causing the other? Do great video gamers become surgeons? Maybe not. It might just happen that those two things require good video game skills, but it doesn't necessarily mean that surgeons are anyone who plays video games is going to be good at surgery. Swedish speakers are healthier than Dutch speakers. Again, not sure if that's true. And that's it. So there you go. There's just a little bit of food for thought. But please, when you leave this course and you're going to forget so many things, please continue to ask the people around you and the things you read and see. Is correlation? Is this correlation? Is this causality? And we, in this age of fake news, you guys have to be more aware of this than ever before. So good luck with this in life, and we'll see you next time.